What if I told you there are monsters lurking in the depths of space so powerful they could devour our entire solar system without a second thought? Not science fiction. These are real cosmic titans, supermassive black holes, with gravitational pulls so fierce even light can't escape their grasp. Picture this, a single one of these behemoths can weigh billions of times more than our sun, warping the fabric of spacetime itself. They're not just holes in the universe, they're engines of chaos, sculpting galaxies and dictating the fate of stars with their unimaginable power. But here's what's even more mind-blowing: these colossal giants aren't rare. They're hiding at the heart of nearly every galaxy, including our own Milky Way. Some are so vast that if you placed one where our sun sits, its edge would stretch beyond the orbit of Pluto. And yet, despite their terrifying scale, they hold secrets that could rewrite everything we know about physics, time, and the very nature of reality. How do they grow so large? What happens to matter once it crosses their event horizon? And could they hold the key to understanding the origins of the universe itself? That's exactly what we're about to uncover. In this journey, we'll explore 30 astonishing facts about these cosmic leviathans, from the way they bend light into surreal rings to the deafening roars of their collisions echoing across billions of light years. You'll discover black holes that spin at nearly the speed of light, ones that shoot jets of superheated plasma longer than entire galaxies, and even the eerie possibility that some might be older than time as we know it. So buckle up, we're diving into the heart of darkness, where the laws of physics break down and the universe reveals its most jaw-dropping mysteries. By the end, you'll never look at the night sky the same way again. At the far reaches of our observable universe, lurking 10.4 billion light-years away, lies a true colossus, Ton 618. This isn't just a supermassive black hole, it's an ultramassive monster weighing in at a staggering 66 billion times the mass of our sun. To put that incomprehensible scale into perspective, if you swapped our sun with Ton 618, its event horizon, the point of no return would stretch well beyond Pluto's orbit, engulfing our entire solar system with room to spare. But what makes Ton 618 truly terrifying isn't just its size, it's the sheer energy it unleashes. This beast is a quasar, meaning it's actively devouring matter with such fury that its accretion disk glows brighter than entire galaxies. Picture a whirlpool of superheated gas and dust spinning at nearly the speed of light, radiating energy so intense that it outshines the combined light of every star in its host galaxy. Even from billions of light-years away, astronomers can spot its brilliant beacon cutting through the cosmic dark. Here's the chilling part: that glare we see today. It's a 10.4 billion-year-old snapshot, meaning we're witnessing Ton 618 as it existed when the universe was barely a toddler. By now, it might have grown even larger, feasting on stars, gas, and perhaps other black holes in a feeding frenzy that reshapes its corner of the cosmos. Yet despite its appetite, this titan isn't unique. It's just the largest we've found so far, a reminder that the universe always has bigger, darker secrets waiting to be uncovered. Scientists have long puzzled over how supermassive black holes grow so unimaginably large, and the answer might be even stranger than you think. One leading theory suggests these giants could form from the direct collapse of enormous primordial gas clouds in the early universe, clouds so massive they bypassed the star phase entirely, collapsing straight into black holes hundreds of thousands of times heavier than our sun. Imagine a cosmic shortcut where gravity wins so decisively that nuclear fusion never even gets a chance, just an instant, dark behemoth born from pure chaos. But there's another possibility: mergers. Like galactic cannibals, smaller black holes could have spent billions of years smashing together, growing larger with each violent collision. Picture two black holes locked in a deadly dance, spiraling closer until they finally merge in a burst of gravitational waves, creating an even more massive monster. Over time, these mergers could stack up, building black holes of staggering proportions while devouring nearby gas and stars for extra fuel. Here's the real mystery, though: some of these giants existed shockingly early, when the universe was barely a toddler. How did black holes weighing billions of solar masses form so quickly? That's the seed black hole problem, and it keeps astronomers up at night. One wild theory suggests the first black holes were born from supermassive stars far larger than any we see today. Stars that lived fast, died violently, and left behind monstrous seeds that grew even hungrier with time. Whatever the truth, these cosmic titans defy expectations, challenging our understanding of how the universe built its most terrifying giants. To grasp the sheer scale of a black hole's event horizon, the point where nothing, not even light, can escape, let's start with Sagittarius A star, the relatively modest monster at the heart of our Milky Way. Its event horizon spans about the width of Mercury's orbit around the Sun, a region roughly 15 million miles across. That might sound enormous, but it's practically a pebble compared to the supermassive black hole at the center of the M87 galaxy. That behemoth's event horizon stretches to the distance of Neptune's orbit, swallowing a region over 6 billion miles wide. Imagine our entire solar system, from the Sun to its icy outer reaches, reduced to a feeding zone for a single cosmic predator. Now take a deep breath, because Ton 618 makes even those giants look tiny. Its event horizon spans a jaw-dropping 1,300 astronomical units. To put that into perspective, if Earth's event horizon were the size of a marble, Ton 618's would loom as tall as a 5-story building. At that scale, light itself would take weeks to cross from one side to the other, trapped in a gravitational prison with no escape. Here's what's even wilder: these event horizons aren't solid surfaces. They're invisible boundaries defined purely by gravity's unbreakable grip. Step over that line, and the universe as you know it ceases to exist. Time distorts, space stretches infinitely, and matter is torn apart atom by atom. Yet from the outside, these black holes appear almost serene, their true violence hidden behind the ultimate cosmic illusion. The next time you look up at the night sky, remember, some of those pinpricks of light might harbor darkness so vast it defies comprehension. What happens when you get too close to one of these cosmic monsters? Time itself begins to unravel. Near a supermassive black hole, gravity warps space-time so severely that clocks tick at drastically different rates compared to the rest of the universe, a mind-bending phenomenon called time dilation. Picture this: if you could hover just outside the event horizon of a black hole like M87 star, where gravity is strongest, a single minute for you could equal years passing back on Earth. Your loved ones would grow old while you barely aged, trapped in gravity's relentless grip. This isn't just science fiction. Remember the haunting scenes near Gargantua in Interstellar, where hours on the water planet meant decades elsewhere. That was based on real physics. Near M87 star, the black hole we've actually photographed, photons of light struggling to escape its accretion disk can take weeks just to climb away from the event horizon from our perspective. Down there, time crawls so slowly that the universe outside would seem to speed forward in a blur. But here's where it gets even stranger. If you cross the event horizon, time dilation becomes infinite. To an outside observer, you'd appear frozen at the edge, your last moments stretched across eternity, while for you, well, physics as we know it breaks down entirely. Black holes don't just bend time, they shatter our understanding of it, revealing a universe far more bizarre than anything we experience in our tame corner of space. These aren't just cosmic vacuum cleaners, they're time machines, warping reality itself with their unimaginable gravity. Imagine floating feet first toward a black hole. The force at your toes would be exponentially stronger than the pull at your head, stretching you like cosmic taffy in a process gruesomely nicknamed spaghettification. Near a stellar mass black hole, this tidal force is so extreme it would shred a human body in milliseconds. The difference in gravity between your head and feet, just 6 feet apart, would create thousands of gs of tension, pulling you apart atom by atom before you even cross the event horizon. But here's the twist: supermassive black holes are gentler killers. Their immense size means their gravitational pull spreads out more gradually. Near Sagittarius A star, for example, you could theoretically survive spaghettification for nearly an hour before reaching the rip point. The tidal forces near its event horizon are weaker because you're orbiting farther from the central singularity, like falling into a wide valley instead of plunging down a cliff. To put numbers to the nightmare, scientists calculate the spaghettification threshold using the black hole's mass. For a small 20 solar mass black hole, you disintegrate about 200 miles from the center, experiencing forces equivalent to hanging from a rope tied to 1,000,000 elephants. But near a supermassive black hole like Ton 618, that threshold shifts inward by thousands of miles, giving you a horrifyingly scenic, if brief, final tour of relativity's cruelest effects. Your last moments would be a slow-motion nightmare, watching your limbs elongate like melting wax as space-time itself twists around you, even stranger. If you fell into an ultramassive black hole, you might not even notice the moment you crossed the event horizon. The tidal forces could be mild enough that you'd still be intact when the laws of physics as we know them cease to apply, leaving you trapped in a place where you no longer exist in any recognizable form. Spaghettification isn't just about being torn apart, it's about unraveling the very definition of existence at the edge of a black hole's hunger. Deep in the heart of the Phoenix Cluster, a galactic city of over 1,000 galaxies, lies a black hole so enormous it defies belief, a 20 billion solar mass colossus that makes Sagittarius A star look like a speck of cosmic dust. This isn't just another supermassive black hole. It's a hyperactive engine of destruction and creation, blasting out jets of energy so powerful they carve Swiss cheese-like cavities in the superheated gas between galaxies, visible only through the lens of an X-ray telescope. The Phoenix Cluster's central galaxy is like a cosmic tornado, with this black hole at its core acting as the storm's eye. Every second, it devours enough matter to swallow several Earths, funneling it into an accretion disk that glows with the heat of millions of degrees. But here's where things get wild. Not all that material gets consumed. Some of it gets hurled back into space at nearly light speed, erupting as twin jets of charged particles that stretch for hundreds of thousands of light years. These aren't gentle streams, they're tsunamis of energy, punching through the intergalactic medium with enough force to create bubbles so vast they could hold entire galaxies inside them. X-ray telescopes like Chandra have captured these ghostly cavities, revealing the black hole's explosive influence. The gas between galaxies, known as the intracluster medium, is hotter than the core of a supernova, yet this black hole's jets carve through it like a blowtorch through butter. Each cavity represents an eruption so violent it releases more energy in one outburst than our Sun will produce in its entire 10 billion-year lifetime. And just like a hurricane leaving calm in its eye, these jets paradoxically cool the surrounding gas, triggering the birth of new stars in their wake. What's truly staggering is the scale of this feedback loop. The black hole gorges itself, unleashes chaos, then inadvertently sets the stage for galactic renewal. It's a cosmic predator with a strange benevolence, devouring matter with one hand while sculpting the universe with the other. The Phoenix Cluster's black hole isn't just a record breaker. It's proof that even the most destructive forces in the cosmos can be architects of creation. If the Sun suddenly switched places with the Quasar SDSSJ 0100 plus 2802, the night sky would burn brighter than 1,000 noons. This 12 billion solar mass behemoth doesn't just shine, it erupts, converting the mass of entire stars into pure energy with terrifying efficiency. At its peak, this single quasar outshines our entire Milky Way by a factor of 40,000. Blasting out enough light in 1 second to power human civilization for millions of years. But the real shock isn't the scale, it's the physics-defying efficiency. When a hydrogen bomb detonates, only about 0.1% of its mass converts to energy. Even the sun's nuclear fusion only squeezes out 0.7%. As DSS J0100 plus 2802, it's a cosmic factory hitting 40% efficiency, rivaling the theoretical limits of black hole energy extraction. Each ton of matter spiraling into its accretion disk releases the energy equivalent of 400 tons of antimatter annihilation. To match its output, you'd need a sphere of 100 billion suns packed tighter than stars in a globular cluster, all burning at once. The secret lies in the black hole's gravitational vise. As matter falls inward at near light speed, particles collide with such violence that friction heats the accretion disk to millions of degrees. Magnetic fields twist this plasma into jets that punch through galactic gas like a blowtorch through paper, while the rest glows with the thermal fury of a trillion suns. And yet, quasars aren't just destructive, they're cosmic lighthouses. They're light traveling billions of years to reach us, carrying encoded clues about the universe's youth. That glare you see isn't just energy, it's a message from an era when galaxies were newborns and black holes ruled as kings of creation. In the distant galaxy cluster Abell 2597, astronomers witnessed something extraordinary, a cosmic storm of freezing gas cascading onto its central black hole like rain falling into a bottomless well. Back in 2016, NASA Chandra X-ray Observatory captured this surreal phenomenon, revealing giant molecular clouds, some spanning 30 light-years across, drifting toward the supermassive monster at the cluster's heart. These weren't just any clouds, they contained an almost unimaginable 3 million solar masses worth of water vapor, along with carbon monoxide and other molecules, swirling in a doomed ballet around the galaxy's core. But here's the twist, this wasn't a smooth, steady flow. The gas was falling in clumps and streams like droplets in a downpour, with some clouds so dense and cold they defied expectations. Space is supposed to be a vacuum, yet here were pockets of chilly molecular gas, some as frigid as -260 degrees Fahrenheit, surviving just outside the black hole's fiery grasp. Imagine a blizzard raging at the edge of a volcano, a paradox that rewrites what we thought possible in such extreme environments. What's even wilder is how this rain fuels the black hole's appetite. Unlike the steady diet of hot gas most supermassive black holes consume, Abell 2597's beast feeds in fits and bursts. Dense gas clouds spiral inward, only to be shredded by tidal forces, creating a sporadic buffet that lights up the black hole's accretion disk in unpredictable flares. It's a chaotic dining experience, one that might explain why some black holes flicker like cosmic light bulbs instead of glowing steadily. This discovery did more than just add a bizarre weather report to space, it revealed a hidden mechanism for how black holes grow. Instead of just slurping up hot gas, they might also gulp down these freezing downpours, a process that could be far more common than we realized. The next time you hear thunder rumbling on Earth, remember, out there in the abyss, entire galaxies are drenched in showers of star stuff, feeding monsters we're only beginning to understand. Rising like ghostly titans from the heart of our Milky Way, two colossal gamma-ray bubbles tower 25,000 light-years above and below the galactic plane, each one big enough to contain 10,000 solar systems stacked end to end. Discovered in 2010 by NASA Fermi Gamma-Ray Space Telescope, these so-called Fermi Bubbles glow with the eerie energy of particles moving at nearly the speed of light, their edges razor-sharp against the darkness of intergalactic space. But the real mystery isn't their staggering size, it's what they reveal about our galaxy's supermassive black hole, Sagittarius A star, and its explosive past. The leading theory, these bubbles are the aftermath of a catastrophic feeding frenzy. Roughly 2 to 4 million years ago, a blink in cosmic time, Sagittarius A star likely devoured an enormous clump of gas or even a star, triggering an eruption so violent it blasted twin jets of high-energy particles straight through the Milky Way's disk. Imagine a volcano erupting not with lava, but with enough raw energy to punch through the galaxy itself, leaving behind a pair of permanent scars visible only in the highest energy light. The timing matches another clue. Ancient light echoes from the Magellanic Clouds, distant galaxies that still bear the ultraviolet afterglow of what must have been a blinding flash. Our black holes belch of radiation lighting up the cosmos. Yet these bubbles aren't just relics, they're still crackling with activity. Fermi's instruments detect gamma rays along their edges, suggesting particles are being accelerated to insane speeds even now, possibly by shock waves from the original explosion. And here's the twist: similar structures have been spotted in other galaxies, hinting that these eruptions might be a universal phase all supermassive black holes go through. Our Milky Way's quiet, well-behaved center, it's just taking a nap between cosmic tantrums, the most haunting realization. If this eruption happened today, the blast of radiation would sterilize half the galaxy, stripping atmospheres and drenching worlds in lethal X-rays. We're lucky to live in the quiet aftermath, but Fermi's bubbles serve as a stark reminder that the monster in our galactic basement is only dormant, not dead. And when it wakes again, the universe will bear witness to a spectacle of destruction and creation on a scale we can scarcely imagine. Some black holes don't just lurk in galactic centers, they flee them. Take CD42, a 20 million solar mass monster caught in the act of escaping its host galaxy at 5 million miles per hour, fast enough to cross the distance from Earth to the Moon in under 3 minutes. This isn't just a wandering giant, it's a cosmic fugitive propelled by forces so violent they defy imagination. The leading theory, CD42 was once part of a binary black hole system. When its partner collided with another black hole, the merger unleashed gravitational waves so asymmetrical they acted like a rocket booster, kicking the survivor clear out of its galactic home. Picture two black holes spiraling toward collision, their final moments warping spacetime so intensely that the resulting gravitational recoil sent the remaining black hole careening through intergalactic space like a bullet from a cosmic gun. But CD42 isn't alone. Even stranger is 3C186, a black hole 7.5 billion light-years away that's been flung so far from its galaxy's core. Its entire quasar glow now shines from deep in the galactic suburbs. The numbers behind this ejection are mind-blowing. To launch a supermassive black hole weighing as much as 5 million suns, the merger would have needed to release energy equivalent to 100 million supernova in a single directional burst. What's terrifying is how common this might be. Simulations suggest up to 1 in 5 supermassive black holes could experience similar kicks during galaxy collisions, turning them into rogue wanderers drifting through the void. Imagine a black hole massive enough to anchor a galaxy, now untethered, barreling through starless darkness indefinitely, or worse, plowing into another galaxy like a cosmic wrecking ball. These nomads might even explain why some galaxies today lack central black holes altogether. The scariest part, we'd never see one coming. Unlike stars or planets, rogue supermassive black holes give no visible warning of their approach until their gravity starts bending light around them. By then, it's too late. They've already rewritten the fate of anything in their path. These aren't just relics of ancient mergers, they're proof that even the universe's most colossal structures can be exiled by forces beyond their control. Around some of the universe's hungriest black holes, there's a cosmic bakery at work, one that forges not bread but colossal, spinning donuts of superheated gas wider than entire solar systems. These aren't your average accretion disks, they're intricate torus-shaped structures captured in stunning detail by the ALMA telescope, revealing how matter spirals toward oblivion at nearly the speed of light. Picture a whirlpool where gravity's grip is so intense that gas atoms collide thousands of times per second, glowing white-hot as they're stretched into a ring thicker than the distance from Earth to Pluto. What keeps these donuts from collapsing into the black hole? Magnetic fields, nature's invisible scaffolding. ALMA observations of the black hole at the center of Galaxy M77 show magnetic field lines wrapped like a giant spring around the torus, channeling material into orderly streams while flinging excess energy outward in twin jets. It's a cosmic balancing act. Without these magnetic forces, the disk would either plummet straight into the void or explode outward in a chaotic burst. Instead, particles orbit for decades, even centuries, before finally crossing the point of no return. Here's where physics gets surreal. The inner edge of these donuts doesn't just glow, it pulses with X-rays so intense they can evaporate nearby stars. Matter there reaches temperatures over 10 million degrees, hot enough to strip electrons from atoms and turn the disk into a soup of naked nuclei and free-flying particles. Yet just outside this inferno, the outer layers of the torus remain weirdly cool, shielded by dust clouds so dense they block visible light entirely. ALMA radio eyes peer straight through that dust, uncovering a structure where ice crystals, yes, ice, float alongside scorching plasma, all held in perfect tension by the black hole's relentless pull. The most mind-bending detail, these donuts aren't static. Time-lapse images reveal kinks and twists in their magnetic fields, like a writhing snake made of pure energy. Sometimes, entire sections of the torus collapse inward in sudden feeding spurts, triggering bursts of radiation bright enough to outshine quasars. Other times, the magnetic fields snap like rubber bands, launching material clear out of the galaxy. It's a reminder that even the most orderly-looking structures near black holes are battlegrounds, places where gravity, magnetism, and raw chaos dance on the edge of annihilation. Black holes come in two familiar flavors: the stellar mass ones formed from dying stars, barely a few times heavier than our Sun, and the supermassive beasts anchoring galaxies, weighing millions or billions of solar masses. But where's the middle ground? For decades, astronomers hunted for the missing middleweight class, black holes caught between these extremes, and the trail led them to a cosmic oddity named HLX-1, lurking 22,000 light-years from the center of Galaxy ISO 243-49. At 20,000 times the mass of our Sun, this enigmatic object isn't just filling a gap, it's rewriting our understanding of how black holes grow. The mystery of middleweight stems from a cosmic bottleneck. Stellar mass black holes form from collapsing stars, but to reach supermassive status, they'd need to consume an unrealistic amount of matter in the universe's infancy. Intermediate black holes like HLX-1 could be the missing link, stepping stones formed when ancient star clusters collapsed or when early universe conditions birthed unusually massive seeds. Picture a cosmic Goldilocks scenario, not too small, not too large, but just right to explain how supermassive black holes got their start. HLX-1's discovery was anything but straightforward. Initially dismissed as a foreground star, its true nature became clear when X-ray observations revealed bursts of energy 100 times brighter than expected for a stellar mass black hole. Yet it wasn't quasar-level powerful either. It occupied a strange middle zone, flaring erratically like a scaled-down supermassive black hole. Even stranger, it wasn't sitting in a galaxy's core where such objects were expected to lurk. Instead, it orbited far out in the galactic hinterlands, possibly the stripped core of a dwarf galaxy devoured by ISO 243-49 long ago. Here's what makes these middleweights so crucial. They could be the universe's black hole nurseries. If enough of them exist, merging over eons, they might solve the puzzle of how supermassive black holes grew so quickly after the Big Bang. Simulations suggest dense star clusters could forge intermediate black holes through runaway collisions, stars smashing together until gravity takes over, forming a single dark titan. Others propose they're relics of the first generation of stars, which might have been hundreds of times more massive than today's stars, collapsing directly into black holes without supernova. But HLX-1 remains an outlier, a lonely clue in a still unfolding mystery. Since its discovery, only a handful of similar candidates have emerged, leaving astronomers wondering if middleweights are truly rare or just exceptionally good at hiding. Some might be drifting undetected in globular clusters, while others could masquerade as unusually bright X-ray sources in distant galaxies. The hunt continues, with telescopes scrutinizing every anomalous flicker in the cosmos, because these elusive black holes aren't just curiosities. They could hold the key to understanding how the universe's most terrifying giants were born. One thing's certain, HLX-1 proves the cosmos still has surprises up its sleeve. For every rule we think we've nailed down, there's always an exception lurking in the shadows, waiting to upend what we thought we knew. The middleweight black hole mystery isn't just about filling a size gap. It's about uncovering a whole new chapter in the story of how darkness shapes the universe. At the heart of every black hole lies one of the greatest mysteries in physics, the singularity. In Einstein's equations, this is a single, infinitely dense point where space and time cease to exist as we know them, a place where gravity becomes so intense that the very fabric of reality breaks down. But here's the catch: infinity isn't a physical concept. It's a mathematical placeholder, a sign that our current understanding of physics hits a wall. The truth is, nature abhors infinity, and many scientists now believe singularities might not be points at all but something far stranger. Enter quantum loop gravity, a theory that suggests black hole cores could be fuzzy, vibrating spheres no larger than a Planck length, the smallest possible unit in the universe. These wouldn't be infinitely dense, just unimaginably compact, packed with the remnants of whatever fell in. Picture a knot of spacetime so tightly wound that it repels further collapse, balancing on the edge of existence like a cosmic rubber band stretched to its limit. Some models even propose these cores could eventually bounce back, transforming into hypothetical objects called Planck stars, though you wouldn't want to be nearby when that happens. But rotation changes everything. A spinning black hole described by the Kerr solution in general relativity doesn't crush matter into a point. It flattens it into a spinning ring singularity. This isn't a solid hoop. It's a whirlpool of warped spacetime where the laws of physics as we know them invert. Cross this ring, and some theories suggest you might not be annihilated. You could emerge in another universe or a different time, though the tidal forces would likely spaghettify you long before you got that far. The real shock: these ring singularities might be naked, lacking an event horizon entirely in extreme cases. If so, their bizarre physics wouldn't be hidden behind a black hole's shadow. They'd be exposed for the universe to see, violating cosmic censorship conjectures and forcing us to rewrite the rules of causality. Whether points, rings, or quantum fuzzballs, one thing's clear: singularities aren't the dead ends we once thought. They're the universe's way of pointing to a deeper reality, one we're only beginning to decode. For millions of years, something colossal has been pulling our entire galaxy, along with the neighboring Andromeda and countless others, toward an unseen point in space with the force of 1,000,000 billion suns. This cosmic mystery, dubbed the Great Attractor, tugs the local group of galaxies at a staggering 1,400 kilometers every second, yet its true nature remained obscured behind thick veils of interstellar dust in the Milky Way's disk. Only recently have astronomers peeled back the curtains to reveal its hidden engine, the Norma Cluster, a dense swarm of galaxies anchored by a supermassive black hole so powerful it warps the fabric of the surrounding cosmos. At the cluster's heart lies Abell 3627, a black hole with the mass of several billion suns, surrounded by enough hot gas to forge entire galaxies. But its real power lies in its location right at the center of an immense gravitational well where dark matter, galaxies, and intergalactic gas converge like water spiraling down a drain. The combined pull of all this matter creates a gravity valley, so deep it distorts the motion of galaxies across hundreds of millions of light years. Picture a bowling ball placed on a trampoline, surrounded by marbles, except the trampoline is space-time itself, and the marbles are entire galactic superclusters sliding inward. Yet the black hole isn't just sitting there, it's actively shaping its surroundings. X-ray telescopes reveal jets of superheated plasma shooting from its poles, carving bubbles in the surrounding gas and stirring the cosmic pot like a spoon in syrup. This turbulence prevents the cluster's gas from cooling and forming stars, essentially putting the brakes on galaxy growth in the region. The result: a self-reinforcing cycle where the black hole's outbursts keep the gas too hot to collapse, ensuring matter keeps funneling toward the center, feeding both the black hole and the great attractor's gravitational grip. But here's the twist: the great attractor isn't the end game. Beyond it lies an even larger structure, the Shapley supercluster, a mega collection of galaxies whose combined gravity might be giving the Norma cluster an extra tug. This cosmic tug-of-war between Shapley's pull and the Norma cluster's push could explain why our local group is caught in this relentless flow. Some theories even suggest these movements are part of a vast cosmic web oscillation, where galaxies ride waves of dark matter like leaves on a river. What's truly humbling is the scale. The Norma cluster's black hole isn't just a local heavyweight, it's a linchpin in a hierarchy of gravity stretching across the observable universe. Its existence reminds us that black holes aren't just destroyers, they're cosmic sculptors shaping the large-scale structure of everything we see. And as we hurtle toward the great attractor at unfathomable speeds, one thing becomes clear: even our galaxy is just a speck in a far grander ballet where supermassive black holes lead the dance. In 2023, astronomers witnessed something bizarre: black holes playing cosmic peekaboo. Using NASA's neutron star interior composition explorer NICER, scientists detected X-ray echoes bouncing off the accretion disks of several active black holes, revealing a process so erratic it defies conventional models. These weren't just random fluctuations. Entire coronas, halos of superheated particles hovering above the black holes, were vanishing and reappearing in mere days, like lights flickering in an interstellar storm. Take Maxi J1820+070, a stellar mass black hole 30,000 light-years away. Its corona, a seething cloud of electrons hotter than the sun's core, inexplicably collapsed inward before violently rebounding 8 days later. The NICER telescope caught the aftermath, delayed X-ray flashes ricocheting off the accretion disk like sonar pings in a cavern, each echo carrying a fingerprint of the black hole's chaotic geometry. Normally, such coronas dim gradually as black holes consume them, but this was different. The coronas weren't just fading, they were evaporating instantaneously, as if someone yanked a cosmic plug. The leading theory involves magnetic fields undergoing snap reconnection, a process where tangled field lines suddenly break and realign, unleashing pent-up energy. Picture a twisted rubber band that finally snaps, flinging stored energy in all directions. In Maxi J1820+070's case, this magnetic snap might have catapulted the corona's particles straight into the black hole, leaving nothing behind but a faint X-ray afterglow. But the real puzzle: why some coronas reform almost immediately while others stay dark for weeks. Even stranger are the echoes themselves. By analyzing their time delays, researchers mapped the hidden space around these black holes with unprecedented precision. The longer the delay between the initial X-ray burst and its echo, the farther the corona must have been from the accretion disk, like measuring the depth of a well by timing how long it takes a dropped pebble to hit the water. Some echoes suggested coronas floating 1,500 miles above the disk, while others implied structures 10 times that height. What's unsettling is how this behavior challenges our understanding of black hole thermodynamics. Coronas aren't just accessories, they're power plants, converting gravitational energy into X-rays that we detect across the universe. If they can vanish without warning, it means black holes might flicker like faulty light bulbs, their energy output swinging wildly over timescales too short for current models to explain. For quasars billions of light-years away, whose light we see as it was in the ancient past, this volatility could mean their true brightness, and thus their calculated distances might be less certain than we thought. The most tantalizing clue lies in the echo spectra. Certain X-ray wavelengths get amplified more than others during reflection, hinting at heavy elements like iron in the accretion disk. By studying these ion lines, astronomers can gauge how fast the disk is spinning, and in at least one case, the post-collapse corona seemed to alter the disk's rotation profile, as if the black hole's grip on spacetime had momentarily weakened. These observations aren't just academic quirks, they're windows into the extreme physics governing black holes' most chaotic regions, where magnetic fields, gravity, and plasma interact in ways no lab could ever replicate. Every flicker, every echo is a breadcrumb trail leading us closer to answering a fundamental question. Why do the universe's most predictable monsters behave so unpredictably? The corona's disappearances might be cosmic hiccups, or they could be signs of a deeper, undiscovered mechanism ruling black holes' inner workings. Until we catch more of these vanishing acts in the act, the echoes will keep taunting us with more questions than answers. Deep in the cosmic dawn, barely 1.2 billion years after the Big Bang, a black hole was already breaking records. J2157, a 34 billion solar mass monster growing so fast it devours a sun's worth of matter every single day. To put that hunger into perspective, imagine swallowing our entire solar system, planets, asteroids, and all, in under 48 hours. That's the relentless appetite of this cosmic kraken, whose accretion disk blazes with the energy of 25,000 Milky Ways combined. But here's the terrifying math. If you were within 1,000 light-years of J2157, its ultraviolet radiation alone would rip apart your DNA like tissue paper in a hurricane. The X-rays, they'd boil away planetary atmospheres in weeks, reducing any Earth-like world to a scorched cinder. Even from that distance, the quasar's light would outshine its host galaxies, every star combined, casting permanent daylight on any surviving planets, assuming they hadn't already been flash-fried by gamma rays. There's no hiding from such fury. This black hole turns its entire neighborhood into a sterile wasteland, a cautionary tale of unchecked cosmic gluttony. What's truly baffling is how something so massive existed so early. Conventional models say supermassive black holes take billions of years to form, yet J2157 defies logic. It's already a titan when the universe was just a toddler. One theory suggests it started as a seed black hole tens of thousands of times heavier than our Sun, born from the direct collapse of a primordial gas cloud. Others argue it gorged on an entire galaxy's worth of gas in a feeding frenzy so violent it bypassed all known growth limits. The clues lie in its light. When we observe J2157, we're seeing it as it was 12.5 billion years ago, its photons finally reaching us after an epic journey across spacetime. Those wavelengths carry fingerprints of heavy elements like carbon and iron, proof that stars were already living, dying, and seeding the cosmos with metals even as this black hole feasted. It's a time capsule from an era when the universe was a forge, hammering out giants in the chaos of creation. Yet for all its violence, J2157 might hold the key to a cosmic mystery: how the first quasars lit up the universe so soon after the Big Bang. If black holes like this could grow ultra-massive almost instantly, they might have served as gravitational anchors for early galaxies, their radiation clearing the cosmic fog and allowing light to travel freely for the first time. In a way, these ravenous monsters could have midwifed the transparent universe we see today, destroyers that were also, paradoxically, creators. the most humbling thought. J2157 isn't done. By now, 14 billion years later, it could be hundreds of times larger, having consumed entire galaxy clusters in the eons since its light left for Earth. Somewhere out there, in the darkness we can't yet see, this Leviathan is still growing. A reminder that the universe's most extreme engines of destruction are always hungry, always evolving, and always rewriting the rules of what we thought was possible. In 2022, astronomers witnessed something extraordinary, a supermassive black hole exhibiting behavior eerily reminiscent of a cosmic toddler after a big meal. Using NASA's Chandra X-ray Observatory, researchers detected periodic outbursts from a distant galaxy cluster, where bubbles of superheated gas, each spanning tens of thousands of light years, were being violently ejected every few 100,000 years. These weren't random eruptions, they followed a rhythmic pattern like a celestial metronome keeping time across the eons. The culprit, a supermassive black hole at the cluster's core, engaging in what scientists now call black hole burps. Here's how it works. As the black hole consumes surrounding gas, not all that material makes it past the event horizon. Some gets funneled into jets of high-energy particles, which punch through the surrounding interstellar medium like cosmic fire hoses. But instead of flowing steadily, these jets hiccup, building up pressure until they unleash violent bubbles of gas that rise through the cluster like bubbles in a soda. Chandra's X-ray vision captured these structures glowing against the darkness, their edges sharp as knife cuts in the fabric of space. What's bizarre is the clockwork regularity. In the galaxy cluster MS 7358.7, located about 2.6 billion light-years away, astronomers mapped at least 3 generations of these bubbles, each one spaced roughly 250,000 years apart. That consistency suggests a feedback loop more precise than anyone predicted, like a thermostat for black hole activity. When the surrounding gas cools and condenses, it falls toward the black hole, triggering a new feeding frenzy and subsequent outburst. Then, the ejected bubbles heat the gas again, temporarily stifling the inflow until the cycle repeats. The energy involved is staggering. Each of these burps releases the equivalent of 100 million supernovae, enough to reshape entire galaxies. In the Perseus cluster, another system exhibiting this behavior, the bubbles have carved out vast cavities in the hot gas between galaxies, regions so large they could cradle multiple Milky Ways side by side. Yet despite their violence, these outbursts serve a paradoxical purpose. By preventing gas from cooling too quickly, they actually suppress star formation, putting a cosmic lid on galaxy growth. But here's the most fascinating twist. These burps might solve a long-standing mystery about why some galaxy clusters aren't forming stars as fast as expected. Without these periodic outbursts, the gas in clusters would cool and collapse into new stars at runaway rates. Instead, the black hole's indigestion acts as a regulator, heating the gas just enough to maintain balance. It's a self-correcting system where the universe's most destructive forces become unlikely architects of stability. The implications stretch even further. If this behavior is common, and growing evidence suggests it is, it means supermassive black holes aren't just passive monsters lurking in galactic cores. They're dynamic players in cosmic ecology, breathing in and out on timescales that dwarf human history. Their outbursts ripple across millions of light years, shaping the destiny of everything in their reach. And as we peer deeper into the cosmos with ever more sensitive instruments, we're realizing these rhythmic eruptions might be the universe's way of keeping its largest structures in check, one burp at a time. Gravity doesn't just bend light, it plays cosmic tricks with it. Take the Hamilton object, a quasar 9 billion light-years away that appears not once, but 4 times in the night sky, arranged in a perfect cross around a foreground galaxy. This isn't some glitch in the universe's code. It's gravitational lensing at its most extreme, where the gravity of a massive galaxy cluster warps spacetime so severely that it acts like a telescope lens, magnifying and splitting the distant quasar's light into multiple images. The science behind this illusion is both simple and mind-bending. When light from the quasar travels toward us, it passes through the gravitational field of the intervening galaxy cluster, which bends its path like a prism bending sunlight. But unlike a prism, this distortion isn't uniform. The cluster's uneven mass distribution creates multiple bending points, each acting as a separate lens. The result, 4 distinct copies of the same quasar, each following a different path through the cosmic funhouse mirror to reach our telescopes. What's wild is how predictable these mirages can be. Using Einstein's equations, astronomers calculated exactly where the quasar's images should appear based on the foreground cluster's mass. And when the Hubble Space Telescope looked, there they were, matching predictions down to the pixel. Even more bizarre, the images aren't perfect clones. Some appear brighter because they trace a longer, more warped path through spacetime, amplifying the light like a cosmic magnifying glass. Others flicker out of sync. Since each image light takes a slightly different route, changes in the quasar's brightness reach us months or even years apart, turning the Hamilton object into a natural time machine where we witness the same event at multiple stages. This illusion isn't just a curiosity, it's a tool. By studying how the quasar's light splits and warps, scientists can map the distribution of dark matter in the foreground cluster, revealing invisible mass that would otherwise stay hidden. The Hamilton object's 4 images act like cosmic probes, their distortions betraying the presence of matter that emits no light but tugs relentlessly on spacetime. It's as if the universe handed us a decoder ring, letting us read the secrets of its darkest components through the artistry of bent light, and this phenomenon isn't rare. Over 100 similar double quasars have been catalogued, some mirroring their source as many as 12 times. Each one is a testament to gravity's power not just to attract but to reveal, turning the cosmos itself into a lens that magnifies the distant and faint, bringing the universe's most elusive wonders into view. The next time you gaze at a starry sky, remember, some of those twinkling lights might not be stars at all, but ghostly echoes of something far older and stranger, repeating across the eons like a cosmic hall of mirrors. When the Event Horizon Telescope unveiled humanity's first glimpse of a black hole's silhouette in 2019, it wasn't just confirming a century-old prediction. It was revealing a shadow so precise it became a cosmic ruler. The now iconic image of M87 star's glowing halo with its eerie dark center wasn't a photograph in the traditional sense. It was a painstaking reconstruction of radio waves detected by telescopes spanning the globe, combined to mimic an Earth-sized observatory capable of spotting a donut on the moon's surface. But that shadow, the absence of light at the image heart, holds secrets even Einstein couldn't have imagined. The glowing ring surrounding it, called the photon ring, isn't just hot gas. It's light itself bent into a perfect circle by the black hole's gravity. Photons skimming the edge of the event horizon get caught in a cosmic ballet, orbiting multiple times before either escaping to our telescopes or plunging into oblivion. The mind-blowing part, the size of this ring matches Einstein's equations to within 10%, proving general relativity holds true even in the most extreme gravitational environments. For M87 star, that ring spans about 25 billion miles, roughly 3 times the diameter of Pluto's orbit, a measurement so precise it let astronomers calculate the black hole's mass at 6.5 billion suns. But the real surprise came when scientists compared M87 star's shadow to Sagittarius A star, the Milky Way's supermassive black hole. Despite being 2,000 times smaller, Sagittarius A star's photon ring appeared almost identical in angular size when photographed. This wasn't a coincidence, it was proof of scale invariance, a fancy term meaning black holes look like cosmic nesting dolls. Whether you're observing one with the mass of a few suns or billions, the shadow's size relative to its event horizon stays constant. It's as if the universe stamped all black holes with the same shadow blueprint, just scaled up or down. What truly astonished researchers was the asymmetry in these shadows. Both M87 star and Sagittarius A star's rings glow brighter on one side, a phenomenon called Doppler beaming. This happens because the accretion disk spins at nearly light speed, making material moving toward us appear brighter due to relativistic effects, while the receding side dims. By analyzing this asymmetry, the Event Horizon Telescope team did something unprecedented. They measured the black hole's spin rates. M87 star rotates clockwise at about 94% of the maximum speed allowed by physics, dragging space-time around it like a whirlpool in a cosmic bathtub. Sagittarius A star, by contrast, spins more sedately, a revelation that challenged assumptions about how these giants form. The implications ripple far beyond pretty pictures. These shadows act as natural laboratories for testing physics under conditions no earthbound experiment could replicate. For instance, any deviation from Einstein's predicted ring size could hint at exotic physics, extra dimensions, quantum gravity effects, or even flaws in relativity itself. So far, Einstein's shadow holds firm, but future observations with upgraded telescopes might uncover tiny discrepancies hidden in the photon ring's subtle fluctuations. Perhaps most poetically, these images reveal black holes not as voracious monsters but as cosmic mirrors. The light composing their portraits has traveled millions or billions of years, bent into perfect circles by gravity's inexorable pull. In that sense, every black hole shadow is a self-portrait of spacetime itself, a reminder that even the universe's darkest corners can't hide from the light of human curiosity. The universe was still in its swaddling clothes when Euler's J1342+0928 ignited just 690 million years after the Big Bang, so early that the first stars hadn't even finished clearing the cosmic fog. Yet somehow, against all expectations, this ancient quasar already weighed 800 million times more than our Sun, glowing with the fury of a trillion suns. Its existence isn't just a curiosity, it's a cosmic paradox. How could something so massive form so quickly in a universe barely out of infancy? Here's the puzzle. According to standard models, black holes grow by slowly accreting gas and merging with others, a process that should take billions of years. Yet Euler's J1342+0928 defies those timelines. By the time its light reached us, it had already devoured enough matter to eclipse the mass of most modern galaxies. Either our understanding of black hole growth is fundamentally flawed, or the early universe cooked up conditions unlike anything we see today. One radical theory suggests the first black holes didn't grow from dying stars at all. Instead, they might have formed directly from collapsing primordial gas clouds, vast reservoirs of hydrogen and helium so dense they bypassed star formation entirely, imploding straight into black holes tens of thousands of times heavier than the Sun. Picture a cosmic shortcut where gravity skips the usual steps, forging ready-made monsters in a single, violent collapse. These direct collapse black holes could have served as seeds for quasars like Euler's J1342+0928, giving them a head start in the race to become supermassive. But even that might not explain its staggering size. Simulations show these seed black holes would still need near-perfect conditions to grow so large so fast, an endless buffet of gas with no pesky stars or supernova blowing it away. That implies the quasar's host galaxy was a gluttonous anomaly, a place where matter funneled into the center with freakish efficiency. Imagine a cosmic whirlpool where gravity won every battle, dragging gas inward faster than it could form stars or resist the pull. The quasar's light carries more clues. Its spectrum reveals surprising amounts of iron, an element forged in supernova, meaning stars had already lived and died by this point. That's like finding an advanced tool in an ancient tomb. It suggests star formation and black hole growth were already intertwined when the universe was less than 5% its current age. What's truly humbling is how this single point of light rewrites cosmic history. Euler's J1342 plus 0928 proves the universe didn't take its time building giants, it crafted them with terrifying speed, under rules we're only beginning to decipher. Every new observation peels back another layer, revealing an early cosmos far stranger and more dynamic than we ever imagined. Imagine the aftermath of two black holes colliding, an eruption of energy so violent it doesn't just send ripples through space-time. It can literally kick the merged black hole across the galaxy like a cosmic billiard ball. In 2022, the LIGO and Virgo gravitational wave observatories detected something extraordinary. A black hole named GW200129 recoiling from its own merger at an astonishing 5,000 kilometers per second, fast enough to cross the entire United States in the blink of an eye. That's 11 million miles per hour, a speed so ludicrous it defies intuition. This phenomenon, called a black hole kick, happens when two black holes spiral together and merge asymmetrically. As they collide, gravitational waves aren't emitted equally in all directions. Some shoot out more powerfully in one direction, rocketing the newborn black hole in the opposite direction like a cannon recoiling after firing. The math behind it is spine-chilling. The recoil force depends on the black hole's spins and masses, with some simulations suggesting kicks could theoretically reach 10,000 kilometers per second under perfect or horrifying conditions. Now, let's simulate what would happen if one of these runaway black holes barreled through our solar system. At that speed, it wouldn't creep in like a slow predator. It would arrive unannounced, streaking past Pluto's orbit in less than a day. Even a black hole only a few times heavier than our Sun would wield enough gravity to yank planets from their orbits like toys on strings, Jupiter's massive bulk. Irrelevant, its 79 moons ripped away in an instant. The black hole's tidal forces would shred Saturn's rings into spiraling debris, flinging ice and rock across the system in a deadly blizzard. Earth might escape spaghettification barely. A stellar mass black hole's event horizon is tiny, just a few miles across, so unless we lined up precisely with its path, our planet might survive the initial passage. But the aftermath would be apocalyptic. The gravitational disturbance would send Earth careening into a chaotic new orbit, possibly hurling us into the Sun or ejecting us into interstellar darkness. Meanwhile, the black hole's gravity would scatter asteroids and comets like shrapnel, triggering extinction-level impacts across whatever worlds remained intact. The real horror, we might not see it coming. A lone black hole, unless actively feeding, is nearly invisible against the void. By the time telescopes spotted stars warping around an unseen mass, it could already be too late. And unlike in sci-fi, there'd be no dramatic visuals, just a silent, unstoppable force rewriting the solar system's architecture in hours. Yet these kicks aren't just destructive, they're cosmic sculptors. A black hole launched at such speeds could escape its host galaxy entirely, doomed to wander the intergalactic darkness forever. Others might end up in galactic suburbs, far from the dense cores where supermassives usually lurk. These rogue black holes could explain mysterious quasars found far from any visible galaxy, their brilliant accretion disks shining like lighthouses in the abyss. The detection of GW200129's kick was a watershed moment, proof that black holes don't just merge, they can be sent flying across the cosmos by the sheer violence of their own collisions. It's a reminder that even the universe's most massive objects are subject to forces beyond their control, players in a game where gravity writes the rules and sometimes changes them without warning. 6 million years ago, when early hominids were first walking upright on Earth, the heart of our galaxy was erupting with a violence that would have lit up the night sky like a second sun. Today, we see the evidence frozen in time, a trail of ionized gas called the Magellanic Stream, stretching 300,000 light-years behind our neighboring dwarf galaxies, its atoms still buzzing with energy from a cataclysmic event. The culprit, Sagittarius A star, our Milky Way's supermassive black hole, in the throes of an outburst so powerful its shockwaves are still rippling through intergalactic space. When NASA's Fermi Gamma-Ray Space Telescope mapped this ancient crime scene, it found something extraordinary. The stream's gas wasn't just ionized, it was polarized, meaning its light waves vibrated in a specific direction. That's the cosmic equivalent of finding a bullet casing at a crime scene with fingerprints still on it. The polarization patterns pointed straight back to Sagittarius A star, implicating it in an eruption that blasted ultraviolet and X-ray radiation with the force of 1,000,000 supernovae. To ionize gas that far away, the black hole must have briefly transformed into a quasar, shining with the intensity of 100 billion stars. But the black hole left an even bigger smoking gun, the Fermi Bubbles. These twin lobes of gamma-ray emitting gas tower 25,000 light-years above and below the galactic plane, like ghostly hourglasses carved into the Milky Way's heart. Their razor-sharp edges and symmetrical shape betray their origin, a bipolar jet from Sagittarius A star punching through the galaxy's gas, heating it to millions of degrees and filling it with cosmic rays. The bubble's size and energy suggest the outburst lasted anywhere from 10,000 to 100,000 years, a geological blink, but long enough to reshape our galaxy's ecosystem. Here's the chilling part. When the eruption happened, Earth was already teeming with life. Single-celled organisms were thriving in our planet's oceans, utterly unaware that the galaxy's core had briefly turned into a cosmic blowtorch. Had any complex life existed back then, the radiation might have triggered mass extinctions. But the outburst also had a paradoxical benefit by clearing out gas and suppressing star formation in the Milky Way's central regions. It might have created the calm conditions necessary for life to eventually emerge in quieter suburbs like ours. The Magellanic Stream and Fermi Bubbles aren't just relics, they're active crime scenes. Recent observations show the bubbles are still crackling with energy, their edges shimmering with newly accelerated particles. Some theories suggest Sagittarius A star didn't have just one outburst, but a series of smaller eruptions over millions of years, like a volcano with periodic hiccups. If so, the next one could already be brewing deep in the galactic core, a reminder that the monster in our midst isn't dead, just sleeping. And when it wakes, the universe will bear witness to a light show unparalleled in human history. For nearly a century, physicists assumed black holes crushed everything into an infinitely dense point, a singularity where the laws of physics break down. But string theory offers a wild alternative. What if black holes aren't bottomless pits at all, but fuzzy, tangled balls of cosmic strings vibrating with near-infinite complexity? These hypothetical objects, dubbed fuzzballs, rewrite everything we thought we knew about the universe's darkest secrets. The fuzzball concept flips the traditional black hole model on its head. Instead of a smooth, featureless event horizon surrounding a singularity, string theorists propose black holes are packed with vibrating strings extending right to their surfaces like a ball of yarn where every thread buzzes with energy. These strings store all the information of what fell in, solving the infamous black hole information paradox that plagued physics for decades. Imagine throwing a book into a black hole. Under the old model, that book's information would vanish forever, violating quantum mechanics. But in a fuzzball, every letter, every word gets encoded in the vibrating strings at the surface, preserving the universe's information like a cosmic hard drive. What's truly bizarre is how this changes the experience of crossing a black hole's threshold. In Einstein's model, you'd pass through the event horizon unaware, only to be shredded by tidal forces later. But with fuzzballs, there's no inside. You'd collide with a solid-ish surface of vibrating strings almost immediately, your energy dispersing into new vibrations. The difference is like jumping into a pool versus slamming into a brick wall covered in buzzing guitar strings. Astrophysicists are racing to find ways to test this theory. One clue might come from black hole mergers. When two fuzzballs collide, their stringy surfaces could produce different gravitational wave signatures than traditional black holes, subtle vibrations in the after ringing that detectors like LIGO might someday spot. Another test involves studying how matter behaves just outside the event horizon. Fuzzballs should emit slightly different patterns of X-rays as material splashes against their surfaces compared to matter spiraling into a void. The most mind-bending implication: if fuzzballs exist, there may be no such thing as a true singularity anywhere in the universe, just layers upon layers of vibrating complexity, turning every black hole into a knot of cosmic information humming just beneath the veil of spacetime. It's a radical departure from the featureless darkness we imagined, suggesting that even the universe's simplest-looking monsters might be its most intricate creations. What if the invisible glue holding galaxies together wasn't made of exotic particles, but of black holes so ancient they predate the first stars? This radical idea, that primordial black holes from the universe's infancy could solve the dark matter mystery, has been simmering in cosmology for decades. Recent gravitational wave detections and microlensing surveys have reignited the debate, revealing tantalizing clues that some of the universe's missing mass might be hiding in plain sight, disguised as black holes forged in the chaos of the Big Bang. Unlike the black holes we observe today, these primordial relics wouldn't form from collapsing stars. Instead, they'd be cosmic fossils, born in the first second after the Big Bang, when ultra-dense regions of the infant universe collapsed under their own gravity. Picture the universe as a pot of boiling water, where most bubbles pop harmlessly, but a few grow so dense they become permanent knots in space-time. Ranging from an asteroid's mass to thousands of suns, these black holes could be drifting unseen through galaxies, their collective gravity explaining why stars orbit galactic centers faster than visible matter alone allows. The hunt for these shadowy suspects hinges on two key tests. Microlensing surveys like Ogle and Subaru's Hyper Subprime can scan millions of stars for telltale flashes, moments when a hidden black hole's gravity bends and brightens a background star's light like a magnifying glass. If dark matter were made of asteroid mass primordial black holes, we'd see countless such flashes. Instead, these surveys have largely ruled out black holes between a moon's mass and 100 suns as dominant dark matter candidates. The universe remains stubbornly transparent to these gravitational magnifying glasses, suggesting any primordial black holes must either be lighter than an asteroid or heavier than a star cluster. Enter LIGO gravitational wave detections, when the observatory spotted mergers between unexpectedly heavy black holes, some 30 to 50 solar masses. It raised eyebrows. Stars that massive should leave behind neutron stars, not black holes, when they die. But if these were primordial black holes, their unusual mass range would fit perfectly. Simulations show these ancient relics could cluster in dark matter halos, eventually pairing up and merging over billions of years. The merger rates LIGO observes align eerily well with predictions for primordial black holes making up just 1% of dark matter, enough to explain some gravitational wave events without contradicting microlensing constraints. The plot thickens when we consider the cosmic microwave background. Planck satellite data shows primordial black holes heavier than 10,000 suns would have distorted the early universe's radiation patterns, a fingerprint we don't see. Yet loopholes exist. If these black holes formed during brief phase transitions in the early universe, like bubbles freezing in an ice tray, they might have clustered in ways that evade current detection limits. Some theorists propose they could be hiding in the cores of neutron stars, slowly consuming them from within and explaining bizarre astronomical flares. Perhaps the most mind-bending twist comes from quantum mechanics. At tiny scales, primordial black holes could evaporate via Hawking radiation, leaving behind a zoo of exotic particles, or even acting as dark matter's microscopic building blocks. Others speculate they might be cosmic seeds, sparking the formation of supermassive black holes by attracting vast clouds of gas in the early universe. While the evidence remains inconclusive, the implications are staggering. If even a fraction of dark matter consists of primordial black holes, it would mean the universe is threaded with invisible knots of spacetime, relics from its fiery birth. Every galaxy might be swimming in a sea of these dark ghosts, their silent gravity shaping cosmic evolution while remaining forever hidden from our telescopes. The search continues, not just for dark matter's identity, but for a hidden population of black holes that could rewrite our origin story. Imagine listening to the universe's deepest secrets not through telescopes, but through sound waves rippling across spacetime itself. When LIGO detected the gravitational wave event GW150914 in 2015, scientists didn't just see the collision of two black holes, they heard it. By converting the signal into audible frequencies, they revealed a cosmic chirp lasting just 0.2 seconds, a fleeting crescendo as the black holes spiraled together at half the speed of light before merging into a single, more massive void. That chirp wasn't just data, it was the death cry of a star-sized black hole, translated into a sound humans could perceive, but gravitational wave songs come in all frequencies. While stellar mass black holes like GW150914 produce high-pitched chirps, supermassive black hole mergers create something far more ominous, a bass hum so low it vibrates on timescales of years. These frequencies are too deep for LIGO to catch, but they're the prime target for ESA's upcoming LISA mission in the 2030s. Picture a trio of spacecraft forming a million-mile-wide triangle, lasers connecting them like the strings of a cosmic violin, poised to detect the slow, resonant mergers of billion solar mass black holes. When two of these titans collide, their gravitational waves stretch and compress spacetime with wavelengths longer than the distance from Earth to the Sun, producing a drone that could last for months, a single, drawn-out note heralding the birth of a new galactic core. What's fascinating is how these sounds reveal details no telescope could capture. The pitch and shape of GW150914's chirp told astronomers the black holes weighed 36 and 29 solar masses, spinning wildly before impact. The ring-down after the merger, a fading hum as the new black hole settled into its final form, matched Einstein's predictions to within 99.9% accuracy. It's like listening to a bell's resonance to deduce its material, only here the bell is a warped pocket of spacetime 60 times heavier than our Sun. The most haunting compositions might still be ahead. Some theorists speculate that certain black holes could produce harmonic overtones, like musical chords, if their surfaces vibrate in ways that defy classical physics. Others suggest colliding black holes in dense environments might create chaotic noise as they plow through gas and stars, distorting their gravitational waves like a ship's wake churning water. And then there's the eerie possibility of echoes ripples bouncing off hypothetical quantum structures near the event horizon, hinting at physics beyond Einstein's relativity. These aren't just abstract curiosities. By sonifying gravitational waves, researchers have made the cosmos accessible in unprecedented ways. Blind scientists can now analyze data through sound, while public outreach projects let anyone listen to the universe's darkest symphonies. That chirp you hear isn't just a black hole's death rattle, it's the universe reminding us that even its most silent monsters have voices, if only we learn how to listen. In the cosmic blink of an eye, just 670 million years after the Big Bang, the quasar SDSS-J0100 plus 2802 already weighed 12 billion times more than our Sun. That's like finding a fully grown blue whale in a newborn's crib. This impossible giant, shining with the fury of 400 trillion suns, presents astronomy's most perplexing riddle. How did black holes grow so incomprehensibly massive when the universe was still in diapers? Standard physics says massive objects take time to grow. A black hole feeding at the theoretical maximum rate, the Eddington limit, would need nearly 1 billion years to reach 1 billion solar masses. Yet SDSS J0100 plus 2802 shattered that timeline, achieving 12 times that weight before the universe celebrated its 700 millionth birthday. It's the equivalent of a baby lifting a freight train, a feat that defies every model of cosmic growth. The crisis deepens when we examine its environment. Today's supermassive black holes thrive in dense galactic cores, fed by vast reservoirs of gas. But the early universe was sparser, with matter spread thin after the Big Bang. For SDSS J0100 plus 2802 to feast so lavishly, it would have needed to devour gas non-stop at twice the Eddington limit for its entire existence, a cosmic buffet with no pauses, no slowdowns, and miraculously no interruptions from supernova or competing stars. One radical solution proposes that the first black holes didn't grow from stars at all. Instead, they may have formed as direct collapse black holes, primordial behemoths born when giant gas clouds, free of pesky star-forming turbulence, collapsed directly into black holes weighing tens of thousands of solar masses. These ready-made monsters would have started life with a massive advantage, skipping the tedious stellar evolution phase entirely. Imagine planting a fully grown tree instead of waiting for a sapling. That's the head start these cosmic anomalies might have had. Yet even this theory strains to explain SDSS J0100 plus 2802's gluttony. Some simulations suggest early black holes could have broken the Eddington limit through supercritical accretion, where gas inflows become so dense that radiation can't push back effectively. Picture trying to blow out a candle in a hurricane. The black hole's own energy output gets drowned out by the sheer volume of matter crashing in. Under these extreme conditions, a black hole could gorge itself at 5 or 10 times the standard limit, ballooning to impossible sizes in record time. Dark matter might hold another piece of the puzzle. The prevailing theory suggests galaxies form within halos of this invisible material, whose gravity draws in ordinary matter. But SDSS J0100 plus 2802's host galaxy is far too small for its black hole's appetite, like finding a 500-pound gorilla living comfortably in a doghouse. This mismatch implies either dark matter halos in the early universe were anomalously dense, funneling gas to the center with freakish efficiency, or our understanding of how dark matter structures galactic growth is fundamentally incomplete. The quasar's light offers cryptic clues. Its spectrum reveals heavy elements like iron and magnesium, atoms forged in the hearts of stars and scattered by supernova. This means stars were already living, dying, and enriching the cosmos even as this black hole feasted. Yet there's a timing paradox. To produce that much metal, stars must have formed in droves, but their formation should have competed with the black hole for gas, starving it. Somehow, SDSS J0100 plus 2802 thrived amid this competition, as if the universe bent its own rules to forge this early giant. Perhaps the most unsettling implication is that SDSS J0100 plus 2802 isn't unique. Dozens of similar quasars have been spotted in the universe's first billion years, each flaunting the same impossible bulk. They hint at a lost chapter of cosmic history, an era when black holes didn't play by the rules we observe today, growing through mechanisms we've yet to uncover. Every new observation peels back another layer of this mystery, revealing an early cosmos far more dynamic and anarchic than our tidy models predicted. One thing's certain, these ancient giants aren't just outliers, they're cosmic trailblazers. Their existence suggests black holes might have shaped galaxy formation from the very beginning, their gravity carving out niches where stars and planets could later thrive. In that light, SDSSJ 0100 plus 2802 isn't just a puzzle. It's a window into an alternate history of the universe, one where darkness ruled first and light followed in its wake. Crossing a black hole's event horizon should be uneventful according to Einstein's general relativity. You'd glide smoothly into oblivion, unaware of the point of no return. But quantum mechanics paints a far more violent picture, a searing wall of high-energy particles lurking just beyond the horizon, ready to atomize anything daring enough to approach. This clash between physics' two greatest theories, known as the Amps paradox, suggests black holes might be surrounded by deadly firewalls, cosmic kill zones where the laws of physics wage war with each other. The heart of the paradox lies in information. Quantum mechanics insists information can never be destroyed, while general relativity implies anything falling into a black hole vanishes forever. To reconcile this, physicists proposed Hawking radiation particles slowly leaking from black holes that carry away information over eons. But in 2012, Olmary, Marolf, Pulczynski, and Sully Amps calculated a horrifying implication. For this radiation to preserve quantum information, the event horizon must become a blazing inferno. Imagine an invisible curtain of ultra-hot particles, hotter than the sun's core, stretching across the entire horizon like a cosmic bug zapper. Here's why this firewall idea breaks relativity. Einstein's equations describe the horizon as smooth space-time, an unremarkable boundary where gravity's pull becomes inescapable. There's no surface, no abrupt change, just the steady flow of warped geometry. But quantum mechanics demands entanglement. Particles near the horizon must be intricately linked with Hawking radiation emitted earlier. When that radiation reaches infinity, the entanglement must snap to preserve information, releasing enough energy to ignite a firewall. The numbers are terrifying. Calculations suggest firewall temperatures could exceed 10 to the 30 degrees Kelvin, hot enough to vaporize atoms into quark-gluon plasma before they even cross the horizon. This isn't just a theoretical curiosity. If real, firewalls would mean black holes aren't the serene voids we imagined, but cosmic death traps cloaked in a layer of pure annihilation. Yet the paradox runs deeper. If firewalls exist, they violate the equivalence principle. A cornerstone of general relativity stating free fall should feel indistinguishable from floating in empty space. A freely falling observer should notice nothing unusual at the horizon, but a firewall would make their final moments unmistakably violent. This forces physicists into a trilemma. Either quantum mechanics is wrong, black holes destroy information, or general relativity fails at horizons. Some theorists propose wild workarounds. One idea suggests firewalls only form when someone tries to measure Hawking radiation, like a quantum version of Schrödinger's cat where the firewall exists only if you look for it. Others argue the paradox reveals a fundamental flaw in how we think about spacetime, hinting that locality, the idea that objects are only influenced by their immediate surroundings, might break down near black holes. The most radical solution, maybe spacetime itself is an emergent property, stitched together by quantum entanglement like threads in a cosmic tapestry. If so, the firewall marks where those threads unravel, revealing the chaotic quantum machinery beneath. While telescopes can't yet spot these hypothetical infernos, future gravitational wave detectors might catch subtle anomalies in merging black holes that betray their presence, ripples in spacetime carrying the screams of dying physics. For now, the Amps paradox stands as one of science's greatest unsolved puzzles, a glaring reminder that where black holes are concerned, the universe keeps its most dangerous secrets just out of reach. Whether firewalls are real or mere mathematical phantoms, their existence forces us to confront a terrifying possibility. that the cosmos' darkest corners might be stranger and deadlier than even Einstein dared imagine. In August 2019, the cosmos wrote its name in gravitational waves with a collision so colossal it sent ripples through spacetime itself, the event known as GW190521. This wasn't just another black hole merger. It was a record-shattering cataclysm that birthed a 150 solar mass black hole, a beast so massive it defied classification. Neither stellar mass nor fully supermassive, this remnant exists in a cosmic no-man's land, forcing astronomers to coin a new term, intermediate mass black hole. But the real shock wasn't its size, it was the realization that the merging black holes, weighing 85 and 66 solar masses, were themselves too hefty to have formed from collapsing stars. Here's the puzzle. Conventional astrophysics says stars can't forge black holes above roughly 50 solar masses. At that size, dying stars become so unstable they blow themselves apart in pair instability supernova, leaving nothing behind. Yet GW190521's progenitors bulldozed past that limit, suggesting they weren't born from single stars at all, the leading theory. These were second-generation black holes, the products of earlier mergers in a dense stellar environment where smaller black holes paired up, merged, and then found new partners in a brutal cosmic dance. Picture a dark family tree where black holes marry, produce heavier offspring, and those offspring remarry, climbing the mass ladder with each violent union. The merger's dynamics were equally mind-bending. As the two black holes spiraled toward collision, their unequal spins created a gravitational kick so powerful it launched the final black hole sideways at nearly 200 kilometers per second, fast enough to escape most galaxies. LIGO and Virgo's detectors captured the entire symphony, the final orbits lasting mere seconds, the merger's crescendo as the black holes plunged together, and the ring down as the new black holes shed distortions like a bell fading to silence. That ring down held clues to the remnant's shape, initially lopsided like a squashed basketball before smoothing into a perfect sphere of warped spacetime. What makes GW190521 truly groundbreaking is its glimpse into hierarchical growth, a process where black holes build mass through multiple mergers. In the crowded cores of globular clusters or active galactic nuclei, such chains of collisions might be commonplace, forging ever larger black holes like cosmic Russian nesting dolls. Simulations suggest some environments could produce black holes over 1,000 solar masses this way, bridging the gap between stellar corpses and supermassive giants. Yet mysteries linger. The signal's peculiar, short chirp duration hints these black holes might have met on elliptical, not circular, orbits, perhaps flung together in a chaotic gravitational three-body interaction. There's even a tantalizing possibility one or both were primordial black holes, relics from the Big Bang lurking unseen in modern galaxies. Most provocatively, GW190521's remnant sits squarely in the mass gap where black holes were thought impossible. Its existence suggests our models of stellar evolution or pair instability supernova might need revision, or that the universe has more exotic ways to build black holes than we've dreamed. Every ripple from such collisions isn't just a tremor in spacetime, it's a telegram from the dark side of the cosmos, forcing us to rewrite the rules of how darkness grows. Deep within the violent whirl of a spinning black hole's accretion disk, nature runs the ultimate power plant, a process so efficient it could outshine all the stars in a galaxy combined. The Blandford-Xenagic mechanism, named after the astrophysicists who decoded it in 1977, turns black holes into cosmic batteries, harnessing their rotation to spit out jets of energy so powerful they can pierce through entire galaxies. Here's how it works. As a black hole spins, it twists spacetime around it like a vortex, dragging magnetic fields along for the ride. These fields aren't passive. They snap and reconnect, channeling plasma into beams that shoot outward at nearly light speed, carrying away up to 40% of the black hole's rotational energy. To grasp the scale of this energy theft, picture a black hole like M87 star, its jets stretching 5,000 light-years into space. The energy in those beams equals the total output of 100 billion suns, enough to power a civilization for billions of years if it could tap into the flow. Some theorists speculate advanced extraterrestrial civilizations might already be doing exactly that. The concept of a Dyson sphere, a megastructure encircling a star to harvest its energy, pales in comparison to the hypothetical Penrose sphere, where a civilization could dip electromagnetic tethers into a black hole's ergosphere, the region just outside the event horizon where spacetime itself is dragged into rotation. By feeding charged particles into this zone, they could extract energy directly from the black hole's spin, like a water wheel siphoning power from a raging river. The numbers defy belief. A typical supermassive black hole rotating at 90% of its maximum speed stores enough energy to satisfy humanity's current power demands for quadrillions of years. Even a modest stellar mass black hole could provide the energy output of 1 million suns without burning fuel or producing waste. The catch: harnessing this power requires technology beyond anything we can currently imagine, materials that won't vaporize near the event horizon, control over magnetic fields strong enough to tear atoms apart, and a way to beam that energy somewhere useful without frying everything in the path. Yet nature has already mastered the Blandford-Zenagic process. Quasars like Ton 618 use it to fire jets that shape entire galactic clusters, heating intergalactic gas and suppressing star formation across millions of light-years. These jets aren't just streams of particles, they're electromagnetic tsunamis, carrying twisted magnetic fields that accelerate cosmic rays to energies 1 million times beyond what our most powerful particle colliders can achieve. When these jets slam into surrounding gas, they create shock waves that glow across the electromagnetic spectrum, etching intricate filament structures visible in radio telescopes. The most mind-bending implication lies in the black hole's inevitable slowdown. Every joule of energy extracted from those jets comes at the cost of the black hole's spin, like a spinning top gradually losing momentum. Over billions of years, even the most rapacious quasars will run out of rotational energy, their jets fading as they settle into a lethargic, non-spinning state. That's the irony of cosmic power generation. The universe's most efficient engines are also self-consuming, trading their fury for transient brilliance. Perhaps one day, far in the future, some civilization will perch on the edge of a dormant black hole, coaxing the last dregs of spin from a dying giant. Until then, we watch these cosmic dynamos from afar, marveling at the universe's ability to turn even its darkest monsters into beacons of raw, unforgiving power. Even the mightiest black holes are not eternal. Given enough time so vast it makes the age of our universe look like the blink of an eye, these cosmic titans will fade away, their dominance undone by the slow but relentless whisper of Hawking radiation. Named after Stephen Hawking, who first predicted this phenomenon in the 1970s, this mysterious process peels away a black hole's mass particle by particle, until nothing remains but a faint puff of radiation. But the timescales involved are almost beyond human comprehension. Take a stellar mass black hole, one formed from the collapse of a massive star. Left undisturbed, it would take 10 to the power of 67 years to fully evaporate. That's a 1 followed by 67 zeros, a number so large it dwarfs every second that has ever passed since the Big Bang multiplied by 1 billion. To put this into perspective, if you condense the entire lifespan of the universe into a single second, the evaporation of even a small black hole would stretch across trillions upon trillions of those cosmic seconds. But supermassive black holes, the billion solar mass behemoths anchoring galaxies, hold onto their existence far longer. Their sheer size slows the evaporation process to a crawl, extending their lifespan to an almost unimaginable 10 to the power of 100 years. That's a googol, a term coined by mathematician Edward Kastner to describe a number so large it exceeds the total number of atoms in the observable universe. By this point, the cosmos itself will have entered an unfathomable era where stars have long since burned out, galaxies have scattered into darkness, and even protons, the building blocks of matter, may have decayed. Hawking radiation works because quantum mechanics allows particles to pop into existence at the very edge of a black hole's event horizon. Normally, these particle pairs, one matter, one antimatter, annihilate each other instantly. But when this happens at the boundary of a black hole, one particle can escape while the other falls in, stealing a tiny fraction of the black hole's energy in the process. Over eons, this slow leak drains the black hole's mass, causing it to shrink and paradoxically evaporate faster as it grows smaller. The final moments are anything but peaceful. In its last second of existence, a stellar mass black hole would unleash as much energy as 1,000,001 megaton nuclear bombs, a silent, invisible explosion in a long-dead universe. Yet there's a haunting irony to this process. The largest black holes which dominate the cosmos today will ultimately be the last structures to vanish in a cold, dark universe. By the time they finally dissipate, space itself may be so stretched by cosmic expansion that even their radiation will have faded into nothingness, leaving behind a void where nothing moves, nothing changes, and nothing remains. The era of black holes will end not with a bang but with the faintest whisper, a final sigh from the last remnants of a once glorious cosmos. Think about this somewhere out there. A black hole named Ton 618 is so massive that if it replaced our Sun, its event horizon would swallow Neptune with room to spare. 66 billion times heavier than our star, this cosmic behemoth dwarfs our entire solar system with its gravitational grasp. Then there are quasars, cosmic lighthouses powered by supermassive black holes, blazing with the energy of trillions of suns, their light traveling billions of years just to flicker on our telescopes. And let's not forget the primordial giants, black holes that defied logic by growing to staggering sizes when the universe was still in its infancy, rewriting the rules of cosmic evolution before the first galaxies even took shape. These aren't just distant curiosities. These monsters built the universe we know. Their gravity-sculpted galaxies, their jets carved voids in cosmic gas, and their violent mergers sent shockwaves through space-time itself. Without them, stars might never have clustered into galaxies, and without galaxies, planets like Earth might never have formed. In a strange way, we owe our existence to these relentless devourers, the very same forces that could erase a solar system without a second thought. So here's the cosmic perspective. Every time you look up at the night sky, remember, you're staring into a battlefield of titans. Black holes aren't just destroyers, they're architects shaping the universe on scales we're only beginning to comprehend. Which fact left you speechless? Was it the sheer scale of Ton 618, the raw power of quasars, or the enigma of primordial black holes? Drop your answer in the comments, and if your mind's still reeling from these cosmic wonders, hit subscribe. The universe has plenty more mysteries to uncover, and we're just getting